I'm going to go on to talk or discuss the first of two main methods which we're going to be using to solve boundary value problems. And the first method is called the shooting method. And the reason why it's called the shooting method is what we do is we simply guess what our solution is, or what our initial value is for our first order derivative. Okay, so if we're presented with a second order ODE, we split it into two first order ODEs as per normal. We'll have some initial value for y1, but we don't have an initial value for y2. So what we do is we simply guess what that initial value is, and we solve. And so at the upper bound, for our solution, we're going to have some number. And then we adjust our initial guess based upon what that solution is at the upper bound. This is called the shooting method because if you're shooting at a target, let's say you're an archer shooting at a target, and let's say you shoot one arrow and you're a little bit to the left of the target, well, what you're going to do is you're going to adjust your aim a little bit to the right, so hence it's called the shooting method. Okay, so let's have a look at an example. So this is example 5.2. So we've got a second order ODE. So if we split it into two first order ODEs, like so, our initial value for y is 1, so therefore our initial value for y1 is also 1, but we don't have an initial value for y2 because we've introduced y2 into our equation to be able to write it as a system of two equations. So we're going to guess it, and we're going to use the guess value s. So s is some number, and we're simply going to guess it. So what we then do is, using this initial value for our second equation, we are going to solve this system. Okay, so this is done in this this MATLAB code below. Okay, so if I quickly talk through the code. So here we have our ODE function. Note, but we have a system of two equations. So I have an array of two elements. Okay, so the first equation is equal to y2. The right hand side of the second equation is y1 plus y2. We have our t domain, t-span. I've also introduced a new vector called b-vals, which is our boundary values. So this is the solution at a lower bound when t equals 0, and this is the solution at the upper bound when t equals 1. Now I'm going to use three guess values. So I've used a guess value of 1, 2, and 1.5. So I'm going to solve this 3 times, and I'm going to use a step length of 0.2. Okay, so we're going to use a for loop to loop through our 3 guess values, and what I've got here is a function called Euler. Now this is defined usually at the bottom of your MATLAB script. Okay, so this just solves our function f over the value of t-span. We have initial values, so this here is a 2-element array. So b-vals1 is our initial value, our initial solution for y1, and si is our guess value. So when I is 1, we have an initial guess value of 1. Okay, and I'm solving this 3 times, so I'm going to store all of my solutions in the y array. So this code here just appends the current solution, which is y1, onto the end of our array. Okay, if we have a look at the output. Okay, so I've solved this 3 times, so I've got 3 different tables. So this was using a guess value of 1. So you can see the initial value for y2 is 1, and our initial value for y1 was 0. This second column here, this y1 column, you can see we have a value of 1.5856 at the upper bound. So if I go back to our definition of our problem, we wanted a value of 2. So that the solution at our upper bound was meant to be 2, but using a guess value of 1 for y2, we have 1.5868. So we're undershooting the actual solution. So what we do, or what we've done here, is we increase our guess value to 2. So this was our first guess value was 1. Now we're using a guess value of 2, and we solve again. And if we compare our solution for y1 at the upper bound, we got 3.1712, and we were expecting, or we wanted that to be 2. So we've increased our guess, but we're over it now rather than being under it. So what about if we split the difference and choose an initial guess value of 1.5? So do the same thing again, solve, using, in this case, using the Euler method, and we get a value of 2.3784. So we're still over it. So our next, if we're to do this again, we'd probably reduce our guess values to maybe 1.25. And we keep going, we keep solving the problem over and over again until we're satisfied that this final solution is accurate enough for our needs. And then your solution is simply the Y1 column here. Okay, I've plotted this. So these are our three attempts. So this line down here, okay, that was our first attempt. So that was using an initial guess value of 1. And you can see this square is what our target was. So we're always using the same initial value, but that's our target. Okay, the dark blue one, okay, this was our guess of when it was equal to 2, when S was 2, and the red one is when S was 1.5. Okay, so you see we undershot it first, we overshot it, and then we overshot it again. So we keep aiming at the target until we get our upper bound bang on where we need it. Now you can do that by trial and error, up a bit, down a bit, up a bit, down a bit, etc. There's a more clever way of doing it than that. We're going to introduce the secant method. Now you should have met the secant method last year, and this is a root finding algorithm. So if you have some function f and you want to find out the value of s for where f of s is equal to 0, we have this iterative step. So our new value of s is equal to our current value minus the value of f of s, and this is multiplied by our current guess value minus a previous guess value divided by the function using the current value minus the function using the previous guess value. So si and si minus 1 are current and previous guess values for s. Si plus 1 is an improved guess value. And like with iterative methods, we continue until the difference between two guess values are less than that, some small number, which is tolerance. Now, for our purposes, we want the solution of y dash t max to be equal to the upper boundary. So we define our function as being the known solution. Sorry, this is our calculated solution minus the known solution. Okay, so here's the shooting method using the secant code. Okay, so what we do is we need to start with two guess values. So here I've started with a guess value of S0 is our old guess value, S1 is our new guess value. So old guess value of 1, new guess value of 2. So that's just to start things off. And f of 0 is 1. Again, that doesn't matter what that number is, it's just so we got a number defined to start things off. So we've got a for loop, which is going to loop through 1 to max iter. So we don't, sometimes sometimes the shooting method doesn't converge, so we want to stop it after some iterations. So max iter is just an upper bound for the number of iterations we're going to use. Okay, so then we solve using some ODE solver. So this could be Euler, it could be an explicit Runge cutter, it could be implicit Runge cutter, it could be a multi-step method, doesn't really matter, ODE solver. Using the standard, so f is our function, ODE function, t-span is our domain, and we have our initial values. So we have the lower bound, the boundary value for the lower bound, and then we have the boundary value for our guess value. Now we use the secant method. Okay, so f1 is going to be the difference between our solution and what we're aiming for. So our solution, which was calculated using our ODE solver, is here. bvals2 is what we're aiming for. Okay, so we want this to be 0. So we're finding the roots of this essentially. So using the secant method, which is here, okay, so equation 5.3, okay, so I've updated the guess value using those values there. And so once I've calculated the new guess value, I update the old one. So for the next iteration, the old value is going to be S1. The current value is going to be S2, which I've just calculated. And we also update F0. So we need to check for convergence as well. So when the S1 and S0 are very close together, some tolerance I suggested 10 to the minus 6, we're going to break this for loop. Okay, so let's have a look at an example. So we're going to use the boundary value problem from example 5.2. So we're going to solve this one here using the secant method. Scroll all the way down again. Where were we? Okay, so I've already got it stored in the memory. So F was stored previously. So this uses this function, which is a shooting method, and I've outputted the table here. Okay, so you can see the shooting method, it ran a few iterations, and you can see, but we have our upper bound solution is equal to 2, which we wanted. So I scroll down, I've plotted that, and we got it here. Okay, so you can see our solution, which in the end, the correct best guess value is, well, I say correct, the optimal guess value is 1.2614. You can see it passes through the lower bound, and it also passes through the upper bound. Okay, so we used the secant method, we iterated until the difference between our guess values was less than 10 to the minus 6. So you think, hang on, that's quite accurate. Well, actually, no. Just because you actually hit the target at the upper bound doesn't mean that your intermediate or your solution within the domain is accurate, because this still depends upon the accuracy of your ODE solver. So in this case, we were using the Euler method. So remember, the Euler methods is only first order accurate. And for this particular BVP, we have this analytical solution. So this is the exact solution. Okay, so what I've done in the notes is I've plotted the exact solution against our numerical solution, which was obtained using the shooting method with the Euler method to solve our ODE. And you can see it's not quite accurate. So the red line is the exact solution, and you can see the Euler method, even though it starts and ends at the same point, in the intermediate region in the domain, we have some error here. Well, one simplest way to rectify that, or to improve that, is to use a better ODE solver. So in this code here, I'm using the shooting method, but I'm using the second order Runge-Kutta method. Okay, so you can see the output, the table of values. Again, we still hit our target by constantly refining using the secant method. And if I plot that, you can see we have a better solution than compared to the Euler method.